In this slide, we are going to continue to talk about sampling. In this example, we basically have f of s is equals to 10. Basically, we are going to sample 10 samples in 1 second. And we are going to sample the same 10 samples per second for different signals. In the first example, in this signal, f is 1 cycle per second. In this, f is equals to 2.5, f is equals to 5, and f is equals to 7.5, and lastly f equals to 10. Remember that the Nyquist sampling says that we must sample 2 times the maximum frequency. Here the maximum frequency is 1, so we should be sampling at least 2 Hertz. But because we are sampling at 10 Hertz, there's no problem because look, all these red points with the stem are the sampled points, and it still reminds us of the underlying 1 Hertz signal. So this is fine. As the signal frequency becomes higher to 2.5 Hertz, basically we have less points to represent 1 cycle, but here we still clearly see that it is 1 sinusoid. At 5 Hertz, so 5 Hertz in fact is the highest frequency that we can sample using fs equals to 10. Look, it is 1 point at the maximum, 1 point at the minimum, maximum, minimum. So at 5 Hertz, we still can see the sinusoid, although it is being heavily sampled. What happened at 7.5 Hertz? The blue line is the 7.5 Hertz. That means in 1 second, we create this blue line repeat 7.5 times. As we are sampling still at 0.1 second, let us see what are we actually getting ourselves into. 1, 2, 3, 4, 5, and so on and so forth. But if you did not see the underlying blue point, you would have think that this could have been the sinusoid, a much slower sinusoid than the actual blue line. This is called aliasing. A signal of high frequency after sampling appears to be a low frequency. Remember, Nyquist says that if I have fs equals to 10, the maximum frequency of my signal that I can correctly represent is fs over 2, 5 Hertz. Once you have exceeded 5 Hertz, then you are in trouble, and basically the sampled sequence will not correctly represent the underlying original signal. In fs equals to 10, it's even worse. You will see that the blue line is the continuous signal of 10 cycles per second. So in 1 second, you can count that there is 10 cycles. And when we are doing fs equals to 10, we are sampling at 0, 0.1, 0.2, 0.3. It all appears as if the underlying signal was a DC signal of amplitude 1. So this is even more obvious of aliasing. So with that, I think we'll now continue in the next slide to talk about how fs and f will give us the digital angular frequency example. So in this example, we begin with fs equals to 16. Here, capital F equals to 1. fs equals to 16 basically means that we are sampling 1 over 16 of a second per sample. If you write the equation, a cosine 2 pi f over fs n, and you substitute f is 1 here and fs is 16 here, you'll get 2 pi 1 over 16, you'll get pi over 8. So it means that at every one sample, we are moving by pi over 8. And across, how many samples? Here? So pi over 8 times big N to get 2 pi, you will realize you need 16 samples. And you can count. There will be 16, rate points before it repeats again. What about here? Now capital F is equals to 2 in the second example. And if you substitute this again into your equations, you'll realize that we are interested in a cosine 2 pi. Here is 2 now on top for the blue line. Fs is still 16. And now we get pi over 4 radian per sample. So that means in one sample, we are moving by pi over 4. In two sample, we are moving by one sample, two sample, we are moving by pi over 2. So we reach the 90 degrees or pi over 2 for the cosine. That's why this cosine will touch 0. Again, move by two sample, one sample, two sample, will reach pi. Alright, so now here in this example, let's count 1 cycle, 2 cycle, 3 cycle, and 4 cycle. So F is equals to 4. So this is 2 pi 4 divided by Fs. Fs is still 16. And now we are getting pi by 2. So this is A cosine pi by 2, the rate points, showing that in one sample we reach pi by 2. So the cosine from here at the maximum at n equals to 0, at one sample it becomes A cosine pi by 2. Okay, so this is how we now interpret the digital frequency, digital angular frequency omega equals to pi by 2 in this example. We next turn our attention to complex exponential.